Here are two more examples of compositions of functions. We're going to again do f of g and g of f, and look at the domains of each of those compositions. I am going to save that till the very end though, because sometimes it's easier to kind of look at your problem as you go to evaluate domain. All right, so the f of g of x, I still prefer to do this even though I'm comfortable with this notation. I like to rewrite it. All right, substitute g minus x, which is this, x squared minus 25. Now, it's tempting to see the square root in both of these squares and to think of that as like, oh, square root and x squares cancel and 25 is 5, right? That is not true. Okay, don't do it. It doesn't work. A quick example to show that, if let's say x were 6, 6 squared minus 25 would be, according to this shortcut that doesn't work, we would say it's 6 minus 5, so we get 1, right? But notice 6 squared is 36 minus 25. That is not 1. That's square root of 11. So, quick side tangent. I know it's tempting. Don't get cancel happy. Same thing with this one over here. You cannot cancel these x's. It doesn't work. Anytime there's plus or minus involved, it's not all product and quotient, multiply and divide. Second guess canceling. Okay. All right, sorry, I had to throw that out there. So we need to f of that, which means substitute that x squared minus 25 into the f function, and the f function says 1 minus x squared. So 1 minus square root x squared minus 25. Okay. Well, square root and square do cancel here because it's this entire square root squared. So I could just evaluate this as 1 minus x squared minus 25. Square root and square cancel. And simplifying, we'd have plus, we'd have plus 25, right? So negative x squared, but plus 25. So we'd get 26 minus x squared. Okay, we need to talk about domain, but let's do this other one first. G of f of x. Substitute f of x, which is this, into the g function. All right, so into the g function, which is square root x squared, right? X squared minus 25. But x is 1 minus x squared now. So distributing this through, we would have, I'm going to kind of do this in my head, we'd have an x to the 4th, and then minus 2x squared, and then plus 1 minus 25. Now, if you need to FOIL this out, go ahead. 1 minus x squared, 1 minus x squared, but you will get this. Okay, equals the square root. So this becomes square root x to the 4th minus 2x squared minus 24. And that is your answer for g of f, but we will in fact need it factored when we go to do domain. So I'm going to just think of what that would be really quick. Let's see. X to the 4th has to be x squared and x squared, and then we need to multiply to negative 24, add to negative 2, so it should be a negative 6, positive 4. Okay. Negative 6, positive. That works. All right. We'll come back to that in just a second. Domain. When we evaluate the domain of these, how I like to do is kind of think step by step. anytime you see a problem area, anytime you see, remember, you're looking out for square roots and you're looking out for fractions. I'll just put numerator over denominator. So right away, I have a square root in this problem. Right, so right away, when I look at g of x, I should think, what is the domain here? This one's a bit tough, but one way to do is kind of just guess and check. So I can see if I plugged in 5, right, 5 squared minus 25 would be 0. That's okay. 5 is what we would think of it like as a critical number. Okay, x can be 5, we'd get 0, that's fine. But try a number below that. Can we do 4? And the answer is no, right? 16 minus 25 would have a negative square root. That leads into imaginary numbers. We don't want that. It's not real. But if I did 6, I would have square root of 36 minus 25. That's okay. So therefore the domain is 5 or greater. Anything greater than 5 works. I'm going to show one more approach to that. Let's do it kind of right here. Let's do it down below. So we could factor this x plus 5, x minus 5. Okay, this is our g function, right? And then I know the zeros would be x equals negative 5, x equals 5. And one way to do this, we do test points. So I'm thinking in a number line, if I choose 5, I get 0. If I choose negative 5, I get 0. And both of those look good. And I'm going to backtrack just a second. I'm above here, this is a good start. Okay, I was not quite done. Because we didn't think about negatives, right? So now if I choose any number in between negative 5 and 5, like if I chose 1 or 4, right? Any number in here is not going to work. But if I chose 6, any number to the right is going to work. However, anything to the left will also work, right? If I choose negative 6, that'd be negative 6 squared. Thinking back up here, right? Negative 6 squared minus 25. That'd be still 36 minus 25. That's okay. So I jumped the gun a little bit in trying to show how to work through it, like just evaluating numbers. We really, especially with squares, we really got to take a step back and think about it. So the domain for g, I did not include the fact from negative infinity to negative 5. Right? It could be in there as well. But if you look at the final result here, the final answer, there's no domain restrictions, right? Like just looking at that f of g, it doesn't look like there are any domain restrictions. But because I couldn't begin with any numbers in here from negative 5 to 5, then I can't end with any of those numbers as well. Because it would have resulted in an error right here and an error right here, right? If at any point in your problem, you can't use that number, it's excluded from the domain, then that needs to follow through all the way. And these square roots can be a bit tricky. We know they cannot be negative, but sometimes there's a bit more work than just eyeballing it. Now, it is important to check the very end as well, though, because you might get an additional domain restriction. In this case, no. Our final domain, the domain of f of g, the composition, is from negative infinity to negative 5, bracket, because we could have 0, union 5 to infinity. All right. Now, that little trick is important for this one as well, and that's why I had this factored here. If we go through it step by step, line by line, right? Do I have any domain restrictions for f? No. Do I have any domain restrictions here? Maybe. Right now I gotta kind of start thinking, how do we look at that? And same thing at the very end. It starts to get a bit tricky. So we want this to be greater or equal to 0. And we also want this to be greater or equal to 0. I'm going to move this to the left. Right, that way, or we want them both to be negative, because negative times a negative would be positive. Anyways, this one, I mean, it gets a bit tricky here. The thing is, and why I wrote this one to the left here, is because this is always positive, right? I don't care what you plug in for x. Plug in a negative, you'll get a positive. Plug in 0, 0 plus 4 is still positive. This always results in positive. And why this, since this is always positive, I know that this part cannot be negative, because a negative times a positive would be negative, right? So that's why I had set it up the way I did. Well, now this tells me that x squared has to be greater than 6, which means when we do square root that x has to be greater than this, greater or equal to square root of 6. Or x could be less than or equal to negative square root 6. Now, again, why is that true? You could think of it the way we did here, right? Think of the values that would actually make that negative. That would mean this x squared is less than a negative 6, right? Say we got 2. 2 minus 6, that's a negative. All right, these can be a bit tricky. So to wrap it up, we didn't have any domain restrictions at the beginning here. We had them at the end. I know that from negative infinity to negative square root 6, or square root 6 to infinity, was the domain at the very end of the problem. But at the beginning, I didn't have any restrictions, where part A was opposite. I had restrictions at the beginning and at the end it didn't look like there were any. So this next example is another one where it's important to think of domain, and something easier, like especially fractions, I don't know, you could usually just see it. I know x cannot be 0 here, right? That would divide by 0. And I know x cannot be negative 1 here. So as we go, kind of keep that in mind. All right, f of g of x. F of g of x. So we need to substitute g 1 over 1 plus x into the f function. Well, that function, we have 2 x's, so this is going to get ugly here for a second. We have 2 of those. So we have 1 minus x, so we need to plug in g. Oops. Started to write f all over. We need to plug in, substitute g, 1 over 1 plus x, all over x, which again we need to substitute g. Now, however you choose to simplify it, I prefer to do this, multiply by the LCD. Okay, get rid of all these fractions now. So when we distribute here, 1 times 1 plus x is 1 plus x. When we distribute here, 1 plus x cancels, we just get negative 1. When we distribute here, we just get a 1. So 1 minus 1 is 0, we just have x over 1, which is simply x. If you look at domain restriction, the final answer doesn't have one, right? F of g, I don't see a domain restriction. However, right here, there was a problem. X couldn't be negative 1 for g. And then as you go, kind of take a look. This would still be a problem here, right? X couldn't be -1, X couldn't be -1. So as you go, you could kind of check domain along the way. But in the long run, overall, I'm not going to use interval notation. I'm just going to say X cannot be -1. Even though our answer is X, X cannot be -1. All right, the second one, g of f of x. So write f of x, which is 1 minus x over x. And then we need to substitute that into the g function. So the g function is 1 over 1 plus x, which is now 1 minus x over x. Again, this is ugly. We have a couple fractions. If you multiply by some version of 1, which is the LCD, in this case we only have an x, so I'm going to multiply the numerator by x and the denominator by x. Okay, so 1 times x is x. In the denominator we would have x, and then here they cancel. So we just get plus 1 minus x. So looking at the denominator, we have x and a negative x, so we just get x over 1, which is again x. Anytime you get f of g and g of f as both x, that is called an inverse. We'll look at that more later though. They're in inverse relation to each other. But we still need to think of domain. Okay, domain along the way. F of x. We had a problem right here. X cannot be 0, right? Which we said at the start. X cannot be 0. If we look along the way, x still can't be 0. But in the end, we don't have a domain restriction. That original restriction has to follow through. We just didn't get any additional restrictions. All right. Last thing, I'd put this little star here. I meant to talk about this in the other video, and really quick, f of g of 1, all that equates to is substituting whatever number they give you here at the very end. Okay, now you can do it as you go. This is equivalent to f of g of 1, so you could do g of 1 to begin with, right? Substitute 1 for x, and then whatever number you get, substitute into f. The reason I don't do it that way and I wait till the very end is because I could list, many problems like f of g of 2, f of g of 3, and I want to evaluate all of these. It's much easier to do this composition and then make that substitution rather than reperforming all of this work all over. And that's why I kind of glance over that where we actually have a number to substitute, because my opinion is I would rather wait to just do it at the end regardless.